So welcome everybody. So today we are very pleased to have Mark Palmer, who will be telling us about the path to an energy frontier Muon collider. And we plan to go with Mark to dinner. We are meeting at 6:30 here in the lobby. So if you want to come, please send me a message before, let's say, 4:30 p.m. so that we can make the reservation.
Okay. Well, thank you all for having me here today. It's a Princeton grad, you know, these are old haunts, so it's been a while since I've been here, but it's always fun to come back. I'm going to tell you a little bit about where we stand in terms of moving forward with a possible Muon collider future, particularly for the U.S. high energy physics program. I'm presently at Brookhaven National Laboratory. I'm chair of the Accelerator Science and Technology Department. I was also a member of the U.S. Particle Physics Project Prioritization Panel over the course of 2023 and into the first part of this year. And so after SNOMAS, the development of a plan to move forward was an important piece of the U.S. program. And the Muon collider played a fairly significant role in our options. So I have a huge number of acknowledgements. I have certainly been part of the Muon collider community for well over a decade. I used to run the U.S. Muon Accelerator program. A lot of the things in here come out of that program. We did a number of different things to look at how muons could be used. This included the International Design Study for a Neutrino Factory, the mice experiment, and after the last European strategy update, the International Muon Collider Collaboration formed, which has taken over a lot of the effort. And we're presently in the process of creating a new U.S. effort at this stage. So specific things in here come out of the SNOMAS multi-TeV collider topical group and its contributors, the Accelerator R&D roadmap in Europe, the Muon Collider Forum at SNOMAS, and the P5 report. So the themes I have are to talk about high energy colliders. I'm going to give a brief perspective on those, where we've been and where we're heading. And talk a little bit about why we're interested in muons and how they can be a vehicle for discovery, but a vehicle that has a few challenges left. And then look a little bit greater detail into the machine concepts for the collider and how we might proceed to go forward. So let me start with the colliders. So where have we been for, I would call it the last roughly 30 to 40 years? We've been looking at machines with proton-proton collisions or at Fermilab proton-antiproton collisions. Those machines have traditionally given us our highest center of mass energy reach, but we're looking at collisions of composite particles, which makes analysis a little more complicated. But there's plenty of discovery potential there via both the electroweak and the strong interactions. Our other methodology has been to look at electron-positron collisions. There we have our point-like fermions. We can do precision measurements in the electroweak sector. And when we consider these machines at multi-TeV energies, they become electroweak boson colliders in effect. So the machines that have been playing a role in this have included machines like Super KKB and the LHC. Where we are looking forward, there are linear collider concepts such as ILC and CLIC, but also large circular concepts such as FCC, which would initially host an electron-positron collider that could directly probe the Higgs. Or in China, CEPC and SPPC, which would be initially an electron-positron collider. In both cases with FCC and CEPC, the plan would be to follow on with a very high energy proton-proton collider, 100 TeV scale. Given the parameters of these machines, there's one very big challenge. We don't yet know how to build the magnets that would be required to reach those energies. This plot, which came from Maury Tigner back in 2001, which was shortly after I started focusing primarily on accelerator technologies, is the Livingston plot. For many years, it was considered to be the equivalent of Moore's law for computer chips. And so what you see here is the constituent collision energy measured in GeV, how that scaled with various machines. And over the course of roughly 30 years, we have this very strong increase going up to the Hadron Colliders. Of course, we got to the aughts and we had the LHC, which is where this tops out. But what you see is the curve is starting to turn over. We were in 2000 working on designs for linear colliders that could go up to the few hundred GeV center of mass, maybe getting to the TeV center of mass scale, but again, we were starting to turn over what we could do. The machines that we're interested in now to look at the energy frontier or to do precision studies are now focused on a fairly broad range of energies and a broad range of timescales. So these include the large circular colliders, which are at the lowest energy point in this plot. And being at the lowest energy point because of the effects of synchrotron radiation, we have a hard limit as to how high energy we can achieve without becoming too large to build. Linear colliders potentially can go to yet higher energies. We have concepts for very advanced linear colliders using things like plasma wake field techniques, which purport to be able to go higher. Muon colliders have been proposed, which cover a very broad energy range. And then up here we have 100 TeV proton-proton machines. So what's happened since roughly the late 90s is progress has become much more challenging. It's a combination of machine complexity as well as costs. And so the real question we were asking during the last SNOMAS process was, what are our options and priorities for the next HEP machine? So at SNOMAS, we saw a number of multi-TeV machine concepts presented from TeV class conventional linear colliders, the proton-proton machines. There were some multi-TeV class lepton ion machines also proposed. And then what I would call the lepton collider energy frontier machines, which included the Muon collider and these Wakefield concepts. These represent the potential paths to the energy frontier, and those are what I will spend most of this talk focusing on. So in terms of proton-proton, you have FCCHH, nominally 100 kilometers. They've just finalized their tunnel layout and come out with a final number of 91 kilometers circumference. The goal is to be operated 100 TeV. That requires operation with dipoles that are at least 16 Tesla field strength. That's about double of what we have in the operating machine today. And it requires development of new technology. In China, SPPC, again, 100 kilometer scale, aiming for a little higher energy. They have made a commitment to use high temperature superconducting technology for their magnets, which is certainly a major R&D endeavor, but that lets them get to the higher energy. Of course, there are some folks who say these are large machines, these have many risks associated with them. We should go with technologies that we consider to be fully dependable today. So how do you do that with a proton-proton machine? Well, we could get up to 500 TeV if we could put a 1900 kilometer machine in the Gulf of Mexico. That would use 3.5 Tesla dipoles, which we could build you trivially today as superconducting magnets. What many of us are not quite so sure about is how do we float that machine and maintain the precision that we want for this.
It's supposed to be underwater?
Yeah, so needless to say, the primary proponent of this is a Texan.
Yes.
It uses a great deal of the technology that's being used for oil rigs today. And so it's saying, oh, we have this great technology, this great industrial base in this area. We'll figure it out. I will say it seems like a bit of a leap. At the same time, there isn't any technology in there that hasn't been used to some degree in industry. And
When I last talked to Peter McIntyre, it was just a little bit before the pandemic.
Mhm.
Back then, he was testing these little thrusters to like
Yes.
keep the.
yeah.
Can you say something about? Do you know?
Right,
anything about
okay,
what's
so,
going on?
yeah, so the
The
issue
question
is,
is just how do you keep it level underwater? And there's, the Navy uses these little thrusters that can apparently keep things
so,
aligned to the sort of millimeter.
oil industry, for various undersea operations now, they have these very nice thruster systems. And, you know, they've done very good things. And as Nima says, this is something the US Navy certainly knows a great deal about. A lot of the water-based industry knows a great deal about. But you also hear the cases where the thruster systems fail in these things. And so if you have 1,900 kilometers of this stuff where you've set, as far as I could tell from what was presented at Snowmass, positioning tolerances that are every bit as aggressive as the most aggressive ones in use. Can you keep 1,900 kilometers of these thrusters running? And I think maybe there's a little bit more risk analysis that needs to be done for this thing.
There's also the 1,900-kilometer extension cord to plug it in.
Yeah, well, okay,
It's also
details.
a problem.
Details.
You have an idea about that too, though. You have an idea that.
Yeah, no, there's.
On the surface of the Gulf of Mexico.
So every question you ask Peter, there is an answer to that. So he did try to think through what all the questions were.
Sorry, why do you want to, sorry, two questions. One, what's the benefit of building it underwater?
So the issue with being on water, in water, doesn't really matter, is where do you get a piece of property that's large enough to put this large of a machine? If you go anything on the surface, you can't get that large an area that is fairly uniform. You're always having to deal with geology and things like that. So floating it was the alternative concept that was presented.
The second question is, you said for China, they were relying on superconductors. So they're saying, assuming that was the statement assuming that you have room temperature superconductors, they can do it, or?
No. So where we are in magnets, and this is in the magnet community, this is a long-standing issue with the National Academy on one of their prior reports, Nina, which is back in, I guess it's been 15 years ago now, there was the report on the potential for room temperature superconductors. We don't build any magnets today based on room temperature superconductors. What happened at the time was we were just making the level of progress that was needed to start demonstrating key features of high temperature superconductors that could potentially operate at liquid nitrogen temperatures instead of liquid helium temperatures. That could be used in the energy grid, that could be used for accelerator quality multiple magnets. And when that National Academy report came out, industrial support for a lot of this stuff bottomed out. And so it actually set back the field probably 8 to 10 years is my estimate. And so we're just at the point really of recovering for this. What's interesting now is high temperature superconductors. If you are listening to the news about the amount of money that's going into compact magnetic fusion. So for instance, Commonwealth Fusion at MIT and the spark reactor concept, we've had a total renaissance of industrial investment in high temperature superconductor. And so in fact, over the last year, high temperature superconductor production for fusion has more than equaled all the quantity of high temperature superconductor created prior to the last year. And so we are starting to get to some industrial scale capabilities there. That's a very good piece of news for these very high energy machines. If we didn't have this industry coupling, it's not at all clear we would have the wherewithal to get where we need. Okay, so we'll get out of the sea and talk about high energy lepton colliders. So there are really two options out there. Arguably the most conventional of the options, in the sense that nearly all of the accelerator systems are straight extrapolations from things we do today, with one notable system that's a real exception, is the Muon collider. Challenge of the Muon collider is putting together an accelerator where we are using decaying beams. And so the lifetime of the Muon and the decay products that are produced end up being the dominating issue for building this type of machine. In addition to that, there are various types of Wakefield acceleration. This is, for instance, laser-based plasma Wakefield accelerators. You may have heard a lot about these. There's also beam-driven Wakefield accelerators, where a high-energy proton or electron beam can be used to create the plasma structures. And then there is very small scale structure Wakefield accelerators that are using things like metamaterials. And we're now talking about putting accelerator structures together in a case like this, where they are at this sub-millimeter scale in terms of what's going on, as opposed to most of our accelerators are using cavities that are macroscopic sized. Okay, so these are the options that were out there. The real challenge for the accelerator community and how we address these things with particularly the experimental community, but also the funding agencies, is how do you evaluate the maturity of the concepts and what amount of work needs to be done? So what's shown here are the various multi-TeV concepts. You see things like FCC-EH and SPPC-EH and UIC, which are the lepton-hadron collider options. In orange, we're not interested in those for the rest of this talk. You have things like the conventional acceleration methods for linear colliders to get you up to the TE scale. This includes things like C-cubed, superconducting concepts like a multi-TeV implementation of an ILC. This includes click. And then you have machines that have the potential to actually go up into what we, in the P5 report, referred to as the 10 TeV parton center of mass scale. This includes collider in the sea, the Wakefield accelerators, the Muon collider, SPPC, FCC-HH. Now, one thing I would like to emphasize, if you want to launch a project in the US, certainly in the US, but similarly internationally, you don't want to be on this chart. You need to be off the right edge of this chart in terms of maturity. Where are we in terms of machines that we could build fairly soon? Well, the furthest to the right is click. We know how to build the technologies for click. We could build a collider. We just don't see a strong motivation since we don't have evidence for supersymmetry.
What happened to the cost estimate of click? Was it more costly than that?
It's not a cheap machine. In US accounting, we are certainly well north of 10 billion. It is a plausible technology if you want to get up to about 3 TeV as a maximum. And that's the weak point with any of the conventional collider techniques. What happens is when you focus the beams down tightly at the interaction point to get the luminosity that's desired, you start to see the impacts of beam straddling. So the useful luminosity that you have, you start having beam straddling at the interaction. The electrons and positrons lose energy, and much of the many of the events that you see now are not actually at the nominal center of mass energy. They are in a long tail of energies below. So the physics leverage of those machines really starts to come apart. If you go through and analyze beam straddling effects for a conventional linear collider, maybe you could produce some useful luminosity up to about 5 TeV, but at that point you've fallen off the edge of a cliff in terms of overall performance. And you have almost, for all the work that you've done to create these very high energy colliding beams, you get almost no events at the nominal center of mass energy. And that's not what physicists need to see. Okay, so in the case of the Wakefield accelerators, you may ask, well, why doesn't that apply? Well, there's a trick that you can play. If you can make ultra short bunches, now we're starting to talk about bunches that may be microns in length scale. You can get into a regime where the effects of the two beams passing through each other, they're so short that it's essentially instantaneous. And we enter a new physics regime that we accelerator physicists call the coherent beam straddling regime. In that regime, you actually get a much higher fraction of your luminosity at the center of mass energy. However, how well do we know that is an open question. You can say the physics does get better on general grounds, but when we actually don't yet have a comprehensive simulation to model the interaction point in those conditions that we have confidence in. So there's a great deal of work to do on the accelerator physics side.
Is there some,
Sorry, I thought I saw another hand come out. Go ahead.
is there some difficulty simulating it? Like why, like if this is a big collider that if this is I've heard Wakefield a lot.
Right.
Like this seems like something you could throw on a cluster.
It's a question of priority, pure and simple. Most of the simulation capabilities for plasma Wakefield are going into understanding the acceleration process and what quality beam we can create at the early stage and propagate to the interaction point. The detailed studies to actually start analyzing the collisions fully. So there are analytical estimates that say in the coherent beam straddling regime, we will do much better than in the incoherent beam straddling regime. Okay, those are very straightforward scalings that we can say, yes, that's the case. At the same time, at these very high energies, there are a lot of secondary effects going on at that interaction point. And it's only in the last couple of years that there's been a really concerted effort to take our codes that were validated basically at the TeV scale for conventional machines and make sure we have properly extrapolated the models to this new operating regime. The hope is over the next 3 or 4 years, those things will get validated to a great degree. But I have, let's just say I've sat through simulations of these things and looking through results and realizing, oh, wait a minute, the extrapolation for this piece was not done right in the model. We need to go back and fix the model. So it's mainly, it needs some more elbow grease more than anything else. Okay. So in terms of this maturity scale, what I will say is things over here on the left, we've only really stated proof of principle stuff. We've not put together the detailed modeling that's required to say that we have confidence in a design. We also haven't done things where we've started to engineer the pieces so that we can confirm performance. And in many cases, it's the engineering that limits the performance on the accelerator, not the fundamental physics. Things in this yellow area are in between. They've started to do those things, but there's still a long ways to go. If we take the examples of FCCHH and CLIC, Like I said, click has been well simulated. We're very close to being able to launch the technology, and it would not take very much to push it over onto the other side for a project proposal at this point. FCCHH, on the other hand, which is kind of into the green area, it's there on the basis that we have basically one major R&D question with in terms of the accelerator, that is, for FCCHH, which is, can we build 16 plus Tesla magnets using, which we're now fairly convinced that that's a little beyond the edge for using niobium 310 technology, which is what we're deploying for the high luminosity LHC. And it may require high temperature superconductor. Okay, when you have a 91 kilometer ring, it sets a level. If you want to reach 100 TeV, there's a minimum field you have to achieve, and it's all or nothing in terms of that energy reach. Okay, we'll touch on that again a little later. But even though this is edging into the green, at best, the R&D program to demonstrate the magnets we would need to build for this, we estimate as being 20 years from now. Okay, so it is still a very long ways to go. Okay, so let me say a little bit about why muons. Well, muons can provide very unique physics reach. They're massive, but they do decay. But this makes them useful in tests of lepton flavor violation, G-2 experiments. They can be precision sources of neutrinos, and maybe a next generation collider. There are opportunities here. They give you the ability to have strong coupling in the S channel for production. So for instance, if you're looking at something like the coupling to produce the Higgs, you can do S channel production with a coupling that's 40,000 times what you get for the electron. They're massive, so synchrotron radiation limitations, which become an issue, for instance, for CEPC and FCCEE, are not an issue. The beams can be produced with small energy spread, and these beam Strahlen effects that we just talked about, again, are greatly suppressed by the energy over the mass to the fourth power. But you have to handle these muon decays. So there are many synergistic things with the collider, from high intensity beams that could be used in the neutrino factory with a very precise composition of neutrinos to be used. And those sorts of things offer staging strategies that may help us get to a collider. And then finally, there are applications beyond HEP. If we had the most intense, brightest muon source available, we would have material science users from around the world coming to get access to those high quality muon beams. These are programs right now that there are major efforts in Europe at PSI, there are major efforts in Japan to produce more beams of that type. Let me spend a few moments on talking about luminosity. And this is important for a muon collider because it doesn't shake out quite the way it does for most other machines. Okay, so the basic luminosity equation that we can write, I would argue this is the most rudimentary version. It scales this n squared, where n is the number of particles in the bunch. You have to look at the collision frequency, and then it's inversely proportional to the beam sizes you can achieve transversely. That's a little more complicated than that. You might have at some point heard about something called the hourglass effect, which is if you have a very long bunch and you start passing them through each other, you'll get focusing from the countergoing beam at the interaction point, and you'll get a squeeze. What it comes down to is you don't get uniform luminosity along the entire length of the bunch. So if you tune up your conditions, you can't get the ideal performance. At the end of the day, we say, oh, it's dependent on sigma x and sigma y. But if you actually want to get the benefit of all of that, you actually have to make the longitudinal length of the bunches be the same size scale as your transverse size. Otherwise, you throw that luminosity away. So it's a little more complicated than a simple scaling equation. For the Muon collider, we convert this to, well, Muon collider typically operates with round beams. So sigma X and sigma Y are the same. We talk about the average square of the bunch charge. Because what's happening is the beams decay away. So you put in counter-rotating bunches in the ring, you watch them decay away. And so then what it comes down to is how many turns are actually producing luminosity. And then how many times do you inject those bunches into the ring? So we now have the frequency of the bunch injection. And again, here over 4 pi sigma squared. So for a 10 TeV Muon collider design, let's have N be 10 to the 12 particles per bunch, which is ballpark of what we think we might be able to do. Sigma is of order a micron, beta star, which gives you, it's the transverse focusing minimum for the beam, but it gives you an idea of the physical size of the bunch that has to be accommodated. So we're trying to get millimeter scale bunches colliding at the IP. Then we have a normalized emittance. So this is the transverse phase space of 25 micron radians. The number of turns that the bunches can interact is determined by the B field in the ring. Smaller ring means you get more times around before the bunches decay. So the number of turns is approximately 150 times the dipole field in Tesla, is the way it works out. What we are looking at predominantly in these designs is having a proton driver that operates with pulses at a 5 hertz rate. So what does that look like? 10 TeV. This comes out to providing about 1.6 10 to the 35 luminosity. And that gets us into an interesting range for physics. Now, this is a crude estimate, but if we're within a factor of 2 or a few of this, I think we can do good physics for the community. The other aspect about this is the beam's decay. So at the outset of the last European strategy, a major question was, well, can the detectors really handle the beam-induced backgrounds? In fact, there's a paper that was published in association with the studies that were done for the last European strategy update, which showed, in fact, you can reconstruct events quite well. This is BB bar production. This was done at 1.5 TeV. But it went through and looked at a whole range of energies and what sorts of resolutions could you have on various measurements. And in fact, these look quite reasonable for producing physics. Other challenges with muons, they're hard to produce. So one of the biggest things that we need, the most effective route to producing copious numbers of muons is through tertiary production of a proton beam on ideally a heavy metal target. What's shown in the movie is the Merritt experiment, which was carried out at CERN, which what you see when you see just a beam going across as a jet of liquid mercury was produced. When you see that jet splash, that's where a proton beam from the SPS struck it. What you should take away from that is when these proton beams strike a material, they have very destructive effects. So a liquid metal jet, which constantly refreshes, is a good idea for this. Environmental rules mean we're very unlikely to use liquid mercury, but there are other options out there. Of course, with the muon's decay, we have to very quickly manipulate the beams that are produced. What comes out of that target is pions. Pions go down a decay channel, they produce muons, There are lots of things that contribute to the overall 60 phase space emittance of the beam. But what it amounts to is you have a bunch that comes out that looks more or less like somewhere between a volleyball and a basketball. Okay, so that's not the sort of bunches we normally think about in accelerators. So we have to cool that down very quickly within the decay lifetime so that we can get some of those, so that we can transport in excess of 10 to the 12th muons to an actual collision point. One other thing that we have to worry about is the decays going into the detector. They create unique backgrounds in a muon detector. I already mentioned that. But then the other thing is that as the muons go around the ring, they decay into electrons and neutrinos. Those neutrinos are sent in the forward direction in a very narrow cone. Some point they have to come out of the Earth's surface. These would be the most intense neutrino sources known to man, except maybe in an astrophysical sense somewhere. But this is neutrinos, which we know they don't interact. We can send them from Fermilab to South Dakota with no problem, no major degradation in intensity. Well, there are so many neutrinos being produced that when they come out of the Earth's surface, enough of them scatter within a radiation depth of the Earth's surface that if you're standing where the neutrinos come out, you're also getting bombarded with ionizing radiation because of the intensity of the beams. Okay, so one of the questions has been, can we manage that and mitigate it? The short answer is we think we have a solution to the problem, but it's a non-trivial problem. Okay, so let's talk a little bit about a collider.
What is the solution? Are you just gonna aim the cones?
Okay, so the issue fundamentally is this narrow cone that's produced. Anytime you have a straight section in your collider ring where you're at the highest energy and the longest storage time in particular, you're generating basically a sweeping flash or a pulsed flashlight beam of neutrinos that where they exit the surface, you'll see radiation effects. If you're just around the ring where you have maybe a very short straight for instrumentation for the ring, it ends up, this isn't a really big deal. A decade ago, we thought we could fix it by simply putting what we call bumps in the beam and have the beam wave up and down. And so now you spread this out. It ends up what you can do at 10 TeV, which is the most extreme case. It's not quite good enough there. You need to be able to wave the beam around by roughly an order of magnitude more than you can do within the vacuum chamber. Okay, sounds like a big deal. Well, back in the day, so before many folks in this room were born, it was standard for us to build accelerators where we put the accelerator magnets on movers. And that was so we could align the machines. But it involved doing macroscopic motions of magnets that were now at the centimeter scale or more. Turns out if you do the same thing in the collider ring, you can get a range of motion that's easily an order of magnitude more than you can do with the beam in the beam pipe with just correctors. And so that lets you solve the bulk of the ring's problem. Basically what it amounts to.
Vibrating.
No, you do it, you don't need to do it quickly. You know, so what we're looking about is getting over radiation limits where if are a problem, for instance, according to European regulations, if you had this stuff coming out near in somebody's yard where you integrated for a year, you exceed the annual radiation limit. So what you can do is once every week or two, adjust the position of the machine, retune your luminosity, and this is not so hard to do. We have plenty of existence cases from the far past. So we think we have it there.
It might be controversial, unfortunately, for public acceptance.
Yes, it is. And that's a huge concern But where we are with this mitigation method right now, so European standards are about an order of magnitude tighter than American standards on this.
Yes.
The mitigation in Europe, we're below the annual thresholds for anything going on. So the fact of the matter is they have a much greater chance of exposure to radon or something like that than they have to neutrino radiation from this source. So,
You're only in trouble if you like stay put on that spot for a year, right?
right, and we'll move it around, so it's not.
Right, but even if you didn't move it around, I mean, so long as it isn't in someone's
It's
yard.
right,
I mean, so it.
but if it pointed into somebody's bedroom, for instance, where they're spending a third of every day, then you start to worry.
Certainly.
Okay.
Sorry, how big is the cone roughly? Like, why can't you just say, I'm gonna buy all of the property along this line?
Okay.
Sorry, I'm
This is what Trump's America is gonna be like.
There is that. Okay. So realize if it were a linear collider and it was all along a straight line, we might have an easier answer. It's this gigantic circle. So it's every little straight section around the circle, because no accelerator is perfectly circular. But along those lines, that's the second part of the mitigation, because where the detector sits, detectors don't like it when you play this sort of game. Okay, we can play with the machine around them, but not the detectors. So the solution at CERN, if they put the collider in the LHC tunnel, is for their preferred interaction point in their preliminary designs, they tilt the detector. One beam comes out in the middle of the Mediterranean. The other beam comes out on the side of a mountain in the middle of the Alps, where, okay, you can't make a case that anybody's going to be hanging out there. I mean, you might have a rock climber there for half an hour, but that's about it. Okay, so.
So we get green mountain goats, you know, and then that's.
My understanding is the cliff face that this thing is coming out. I don't think a mountain goat makes it either. Although I have seen mountain goats on some pretty steep cliffs. In any case, so there is a mitigation that for all the relevant areas. Now, the other issue is some folks don't like that solution. You now have the hottest neutrino beam on Earth that has ever existed. Okay, and so there's a lot more people that say, no, you've got to make at least one of the locations in accessible area, because we want to put our detector there. And so, yeah, in any case, the bottom line, if you'd asked me 5 years ago about this, I would say I was afraid that we would be bumping hard up against legal limits. Where we are now, there are solutions there that the legal limits have gone away. While that still means you have to do the right PR for the communities involved, the risk becomes really quite small.
Is it easier to put like a detector if you put the Muon collider at Fermilab? Is it easier or is it also easy at CERN?
In most cases, because you would want to be deep enough to do things, the exit points are typically outside the site boundaries, because you're at least partway down. So all scenarios that we've considered require going out and buying a piece of property. I don't think that's an insurmountable hurdle.
Like some material like catalyzer in the cone.
Yeah, so this
Stops radiation, but not the.
So the problem is, neutrinos are so penetrating, they're gonna go anywhere no matter what you do.
Yeah.
There is no way to put up neutrino shielding, because you'll still have something nearly intense after the shielding that you do before. And it's anywhere where you have enough material and you go into an air or vacuum boundary that you'll just see copious amounts of ionization coming out. So yeah, there aren't simple things. You know, the shielding you need for this is something we typically refer to as unobtainium. So that's where we are. In terms of the accelerator, okay, what makes it up? Has a proton driver. This is typically a multi-megawatt proton driver, 2 to 4 megawatts of beam that can be put on a target. You have to take this tertiary production, let the beams decay, then you have to turn the beams into bunches so that you can start sending them through a cooling channel. Cooling channel lowers the emittance by nearly 6 orders of magnitude. And at that point, you're ready to put the beams through acceleration stages and ultimately into the collider. Sounds not so hard, but for instance, you have to have very rapid acceleration to avoid muon decays. If you look at a high energy machine like the LHC, you have the opportunity of taking the proton beams up in energy over hours. That's a much easier RF energy equation to solve for how much power you need to put into the system on each pulse than it is for a muon collider. So these machines aren't easy. On the other hand, they fall within relatively straightforward extrapolations of what we know how to do. So,
Mark, can you walk me through that factor of 1 million in the phase space? Because it's like a factor of, well, I mean, naively a factor of 10 in XYZ, PX, BY, PZ is what you're talking about, but going from a volleyball down to a millimeter is already a much bigger factor in at least X and Y. So,
right.
So how does the product end up being kind of the minus
Right,
6?
so what you have to take into account there is in one case, I'm talking about emittance, in one case, I'm talking about physical size. And so when you talk about looking at the very tight focusing that's at a collider interaction point, that's how you get down to the much smaller
Oh, I see.
sizes.
So this is before that.
This is before the focusing, so that's
So you're
the
looking.
disconnect.
Okay, I got it.
Okay, all right, so given that we've had good discussion here, but I'm running behind, so I'm going to keep moving through the slides. So in 2014, there was a P5 panel. The decision was made at the time, the US was going to focus on its long baseline neutrino efforts and other things. And we wouldn't pursue muon colliders anymore. So one of the most common questions I've received is, what's different? Okay. Well, what's changed has been both a combination, there's a different physics landscape today than there was a decade ago. And secondly, there was some key R&D progress. So concept maturity. So where we were in 2013 at the time of the snow mass, there were still issues with being able to operate RF cavities in very high magnetic fields. The easiest way to think about the issues there is if you think of a pillbox cavity where you have an oscillating electric field to drive particles back and forth. It's in a very strong magnetic field. So now if you have any sort of little emitter on the surface of that cavity, in the strong magnetic field, it means the electrons that are produced off that emitter follow a straight line in the magnetic field and hit the other wall. That basically gives rise to a resonance condition where you start to see breakdowns in the cavity, and then it just blows up because you basically start melting your cavity walls. So it's much closer to what you would call an electron beam welder than it is an RF cavity at that point. However, we found out we were working on different cavity materials. The key issue here is, can you come up with a combination of materials and a quality of the cavity surface such that if any dark current is produced this way, that when it goes through, it doesn't have enough energy to actually damage the wall that it strikes, at which point it becomes survivable. So very, very nonlinear sorts of effects going on here. But where we were in 2013, we hadn't demonstrated. Where we were in 2015, we had RF cavities that were working at 2.5 times the specified RF gradients that were required to start building a cooling channel. These are some of the concepts and some estimates of how a cooling channel should perform. This cavity setup, which we demonstrated at Fermilab, demonstrated over 50 megavolt per meter stable operation in a 5 Tesla magnetic field, which is once you get above a certain field, the spiraling of the electrons doesn't change very much. So this is a good limiting case. In addition, the mice cooling channel, which was based at Rutherford Appleton Laboratory in the UK, completed its measurement of ionization cooling. As I said, the other aspect of this is the principles of the cooling channel were applied to various designs that we felt could be engineered to actually get the performance required. The cooling process itself is shown here, and that's worth taking just a moment on. So basically what happens in a cooling channel is you have a solenoid focusing element. You have a particle bunch that has lots of chaotic spread of the beam, where you have individual particle momentum vectors in many directions. Those get focused down into an absorber. And in the DEDX process, the particle momentum is basically lost in its forward going direction. So if you have a transverse element, you bring that back. Then if you follow this with an RF cavity that accelerates in the longitudinal direction, and the goal of this is to restore all the energy that's lost, you end up basically damping out the transverse motion and moving all of this motion into the longitudinal direction. This looks much like the same as the synchrotron radiation damping process in synchrotrons and light sources. So that's how ionization cooling works. The reason we do it in materials is there's no active mechanism. For instance, something like stochastic cooling, which is used in proton machines, that can actually take enough power out of the muon bunches to quickly bring things down.
Haven't you lost about half your muons by like 500 kilometers or so?
Right, so you start at a few times 10 to the 13th muons and that's actually as you enter the cooling channel, as you get to the front of the cooling channel. So you've already lost a bunch more than that before, hence the very high power in the target. Then what you're trying to get to deliver to the collider is going from a few times 10 to the 13th per bunch down to 1 to 2 times 10 to the 12th per bunch. So you're losing over an order of magnitude through the course of the machine. And
to various things.
I
was just thinking about just the decay. I mean,
right. So that's a combination of both acceptance losses and decays, roughly balanced. But it also gives you pause. If you are basically having that many particles decay, it means you have radiation products going into every part of the system. So a major part of this design is the radiation hardness of all the systems. But in fact, we think we understand that at a level that we can go through. I won't say that we've done every inch of the machine. We haven't. On the other hand, we've identified all of the places most sensitive to these losses to analyze whether, for instance, can we shield the superconductor and the superconducting magnets such that we don't get a quench because we overheat it from the radiation losses, because this is a lot of power. Okay, we've also analyzed in terms of the long-term radiation hardness that, you know, the insulator in the magnets doesn't degrade too soon for us to be able to run this machine for 10 years. Okay, so there are things like that that do matter.
But anyway, you lose about an order of magnitude of your muons, but they're still going a few hundred MeV at the end of all of this, and then you boost them up to your final energy.
Right. Yeah. Okay, so, you know, just to quickly go through this, at the target level, we need multi-megawatt targets, high field, large bore capture solenoid. There's ongoing work to do greater than 1 megawatt targets. And what's interesting, the solenoid we need, the capture solenoid we need for this, basically ITER just built it. The parameters there are very close to what we need. So this is a buildable thing. The front end, the energy deposition in the front end components is what we were just talking about. We have RF and magnetic fields, but we've gone through and analyzed those energy losses. That's fine. In terms of cooling, the RF and magnetic fields, when we first were doing this, we were being very conservative and operating, assuming we had cavities that could reach 20 megavolt per meter, which was a low enough accelerating gradient that you didn't have these beamlets of electrons basically damaging the other surface of the cavity because you didn't put enough energy into them. In fact, we were able to push that up by a factor of 2.5 over the course of a 3-year R&D program. You need both high and very high field solenoid magnets up to about 30 Tesla. Parameters for a 32 Tesla solenoid, there's an HTS-based solenoid operating at MagLab in Tallahassee, which has achieved the basic parameters and has the aperture we need. And then we analyze the cooling performance, and we have designs that can achieve nearly all of our goals. Acceleration, this is hard. You have to worry about the acceptance. You don't want to dump lots of beam into your cavities. Basically, we have the elements of design that work, that looks like it scales to everything we need for the TeV scale, but we're still testing. One of the things here is in a fast ramping magnet system, so you're driving magnets through a sinusoid oscillation. If you look at the requirements for the accelerator system as a whole, you're having to shift gigajoules of energy back and forth through that sinusoidal ramp, okay? That's not a trivial engineering thing. It's a great way to melt down lots of stuff. But in fact, we have power supply systems that are starting to meet the sorts of parameters that are required. Collider ring, we would like the highest field magnets we can. We have to worry about shielding the magnets. We have to worry about shielding the detector. And so when this slide was done, we had solid lattices with conceptual design up to 3 TeV. We now have most of that at 10 TeV, and the neutrino radiation studies are showing good results. Finally, the detector backgrounds. And so a key article was this Gents 2020 article, which basically demonstrated that we could get good performance for the physics. The other thing that's changed is the physics landscape. And this is a couple slides I stole from Patrick Mead. But the bottom line is that we haven't seen anything at the TeV scale. The issue, it looks like we need to go well above the 1 TeV scale in order to understand the physics. So what was pushed at SNOMAS was 10 TeV is an interesting next step, and I fully agree with that. One of the things that I think is important for the community is validating that 10 TeV actually has the potential to give us major physics results. But when you look at the physics reach, where you have probes of different things at different energies, whether this comes from the broader discussion of lepton colliders as precision sorts of machines, where you can start to look at specific couplings to a precision level, but also looking at things where you can actually probe things like dark matter and such. There is significant reach scale. The wrong button. Okay, so let me quickly start running through where things went to as these changes went in. So in the European strategy, there was considerable interest in the lemma concept, which was, can we produce low emittance muon bunches with positrons? The challenge of that comes down to something we've been fighting for 40 years when thinking about muons, is how do you make enough of them? Okay, and it can produce low emittance, but not enough for a collider. So our coming out of the European strategy, in Europe, we had an accelerator R&D roadmap that described a technically limited program to validate in muon collider concepts with a 20-year goal. Okay, so that makes it competitive with any decisions for a proton-proton machine, and it is a viable sort of goal. The International Muon Collider Collaboration was established. I won't spend any real time here, except to say that all folks are welcome to join. Institutes and universities can sign on to their memorandum of collaboration. And it's currently hosted at CERN, but that may change over time. This technically limited schedule was aimed at being able to start thinking about things in the 2040 timeframe. One of the key parts of this was to put together a cooling demonstrator, which the hope was to start building a cooling demonstrator before the end of this decade. So let me go through a very lightning survey in our last few minutes here of progress. These are the muon collider parameters that were developed by MAP. We concentrated on things from looking directly at the Higgs resonance with S channel production all the way up to, we had a 6 TeV design. When IMCC came together, the choice was made to look at the 3 TeV design. That was a good connecting point, both with past MAP work and gives a relative comparison point with design studies like CLIC. But then to focus on what could be built at CERN. So this included a 10 TeV and a 14 TeV option. One thing that I will point out is that we are looking here at luminosities that are in the 10 to the 35th range. In order to get those luminosities, we're talking about even up at 14 TeV center of mass having 20 megawatts of power in the muon beams. If you look at what's needed for a 3 TeV click design, that required 28 megawatts of beam power to produce the luminosity. So it ends up that as you go to higher energies, the performance of a muon collider in terms of wall plug power ends up being very good. One way to look at this is the so-called energy efficiency plot, where we're looking at the integrated luminosity per energy that has to be put in the beam. And so what you see with the muon collider is it's climbing very nicely. And once you get up to the several TeV scale, looks very good. These other points are the effective performance that you can expect out of other types of machines, whether it be a proton-proton machine or electron-positron collider.
What's the wall power to get 20 MeV and 20 megawatts in the beam?
The wall power in that case is a little over 300 megawatts. So it's pretty reasonable in terms of any of the things we're looking at going forward. So there's been a great deal of
Mark, there's another question?
Oops, sorry. Go ahead.
On this side, what's the technical jump between 10 TeV and 14 TeV?
Okay, so 14 TeV happens to be something that's it's a well-optimized energy for the LHC tunnel. So that stays in the discussion as a result, okay? The active work, and it is interesting in the sense that when you start to look at this beam power type comparison, it's a good example to look at, but most of the effort right now is going into the 10 TeV design. There's been a huge amount of work going on this. And so this is really just an eye chart of some of the recent accelerator development, which I won't inflict every detail on you. But for instance, this mover and support system study that was done at CERN, this brings those neutrino radiation issues offsite under control. There's been a great deal of work on the machine detector interface to try to optimize the beam-induced backgrounds that you see in the detector, and those are all looking very promising. What I will say in terms of those backgrounds, because they're from tertiary and quaternary particles, stuff that's gone through many stages of interactions coming in, they don't look like real physics tracks. So it ends up that they don't, well, you have to have detectors that can handle occupancy. They don't actually fool you in the physics nearly as badly as people originally assumed. And that was a big step forward. There's been design work on the proton complex, target studies. Here's a picture of the ITER solenoid that nearly meets what we call the threshold parameters for the Muon collider proton driver. It's a 1.7 meter diameter solenoid, which is just fine from our perspective. This one was designed to operate at 13 Tesla. We would like it to operate at a minimum of 15 Tesla, but that's within the range that we can get there with a minor extrapolation. We've talked a little bit about the Muon cooling channel. When you talk about the path through the phase space where you're starting out up here with those big volleyball-sized beams, and you work it through to actually having emittances that are needed for a collider, this is the complicated path you take. One of the things earlier this month, there was a meeting at Fermilab to talk about actually building a Muon ionization cooling demonstrator. You can see roughly the idea of what such a structure would look like. What's being proposed is about a 50-meter long section out of the roughly 1 kilometer cooling channel, 1 kilometer 60 cooling channel. It's instrumented, would have a high intensity source. This gets you potentially about a factor of 2 in cooling, that first factor of 2 where you really measure it with beam parameters. Lots of technology and simulation work to try to understand, including things like collective effects throughout the machine. Can we really get the performance? And so far, all of these have been coming out quite promising. Again, the statement is most of the technology is a relatively straightforward extrapolation of what we do. The special thing is just the muon decays and the need for cooling.
If we go back to that one with your factor of 2, so the idea is that's 50 meters, you said? Right?
Yeah, so this is approximately a
So
50-meter
so
long
2 to the
section.
20 is 10 to the 6. So that's the idea, that nothing new happens? You just do it over and over again?
It's a little more complicated than that, but you do it over and over again with progressively tightening focusing functions. Okay, and the issue is the equilibrium emittance is determined by how tightly you can focus the beam in the absorber. So it does have a progression, which is very important.
But I guess I'm asking, are people going to complain that you have to do it, that there's yet another effect you have to worry about so this is a factor of 2 with everything, right? With the punches in, everything, not.
So the challenge is here. Fundamentally, when we talk about the cooling channel, there are 2 issues. I think we can reduce it to 2 relatively simple issues. One is an engineering challenge, which we have to integrate high field solenoids with RF cavities in a way that we can achieve the lattice parameters that are required. Okay, that's something we're working on, and I would argue that just requires us to do a good design study. The second piece of it is, as you go through this emittance reduction, we understand the beta blocker relationships. There's no magic there, frankly. We understand having the cooling power that's required. What we can't say with absolute certainty is as this emittance reduces using a well-understood theory, do we get to a point where there are additional physics effects that kick in? And so when you talk about going to the 6 orders of magnitude instead of the factor of 2, that will be the objection that's immediately raised. Now, how do we address this? Well, we can build the elements, the engineering part. I've got a bunch of talented engineers on my team. They'll figure out that problem. I'm completely confident how to build the thing. The ultimate performance, the problem is it's a chicken and egg problem in that you don't have these ultra high intensity muon beams until you have these ultra high intensity muon beams, basically. And when you need to make billion-dollar investments to get them, okay, that's not a recipe for success with the Department of Energy.
I'm asking a dumb question, like, so
Yeah.
if there's gonna be a complaint at every stage, why not go till you get like a tenth rather than a half? At least so it looks more parametric.
Cost. Okay, so what we're talking about here is something that's gonna be probably for the US investment would be a couple $100 million to $400 million scale with some in kind from Europe. Okay. The thing about it is if you then want to go through and look at the performance at very high intensities, we don't have muon beams that meet the parameters. We certainly do have proton beams that are intensities of well over 10 to the 13th per bunch that I can go to Fermilab and get. Okay. One of the things we had started at the end of the MAP program was starting to do those studies with proton beams so we can say we've studied the physics in an ionization cooling channel at the ultimate charge densities we're interested in. That will be the thing that I think tips the balance that says people believe it. Okay, so again, huge amount of R&D. One of the interesting things that's going on is there's now 2 detector concepts being pursued for the 10-TeV machine. The music concept, which is European driven, and the Maya concept, which is now a US detector, turning into a US detector collaboration. And so both of these groups, they're working very closely together. We're working on variants on the technology and the machine detector interface to try to get the best physics performance out. I've already showed you some of these working parameters, but these are the ones that continue to be iterated on with different variations depending on how aggressive we want to be. What I will say, and then here's just a simple little schematic showing you, so this is a 10-TeV collider ring. This is the 10-TeV accelerator ring. This is the FCC. This is the LHC scale. This is the click scale. So just to give you a quick pictograph of the size of these various things. So we think this is interesting. So just to finish off, SNOMAS process, was a proposed US program that was presented to P5. This was looked at. This would basically balance the level of effort underway in Europe. In the P5 panel, this was taken very seriously as we're interested in achieving the 10-TeV parton center of mass scale. One of the few options that really fits into the US footprint with Fermilab is a muon collider. And so that was the muon shot referred to in the P5 report. In order to get there, we need a vigorous R&D program. That's the part that we're struggling to get off the ground now. It's difficult in the current funding environment. But we're continuing to work on DOE, and there's a HEPAP meeting next week where further discussions will happen. So just to conclude, there is a 10-TeV parton center of mass muon collider R&D effort underway. It's strongly supported in the US P5 report. What's a critical next step is engagement of the US community with Europe and the international efforts so that we actually can achieve critical mass to pull it forward. And that will be an important input to the third update for the European particle physics strategy, which is there are challenges, particularly the funding. It will take time to ramp up a well-managed effort. We need to put international agreements in place. So for instance, lab researchers can't actually collaborate directly with IMCC at the moment because of the nature of the US CERN agreement. In more broadly, there is development of a US Collider R&D program to oversee all of these things. So we're looking forward to growing a team that can push this forward. In closing, I will say thank you for the attention. I've run a little long. I apologize for that, but I think we did have some good discussion here. This shows you the scale of a Muon Collider complex at Fermilab. What I do want to point out is we are planning on having a Muon Collider school. It will be in the Chicagoland area, August 3rd to 6th of next year. And it will be followed immediately by a Muon Collider community meeting, August 7th and 8th. The other thing I should mention is there is an IMCC annual meeting, which will be held at Daisy next May. So though everyone, it's an open invitation to if folks want to find out more. Thank you very much, Pete.
The collider ring touching the red ring.
Okay. So it's always, so typically we show them touching. It's always the case you have to have transfer lines before them, so touching is not really completely accurate. What's actually going on in this case is they're trying to lay out the collider ring. They're trying to fit this final ring on site, so you see the scale of it. It stays just within the site boundaries for the RCS. The collider ring is overlaying the Tevatron tunnel. And so, you know, if they wanted to go down and do engineering, they probably would push down there because there's conventional facilities close by. So there'd be a little bit of juggling of the design as a result.
This last point you were making about the proton beam, the high intensity proton. So you're saying that like ignoring the mass difference for the moment between protons and muons, we do have proton beams which have the comparable intensities and they're not unstable. So if there's a problem, there still might be a problem getting there, but the final state exists and doesn't have some intrinsic instability or.
So the collective effects scale nonlinearly within, so that the critical thing is to get the bunch intensity up. In terms of the mass difference, if we see collective effects, I think we can model the differences between the proton and the muon, where that corresponds to a very small extrapolation on something that is, you know, when we've had to fight collective effects with any machine, it's strongly nonlinear, so you'll get the nonlinear.
So what are the collective effects for proton beams, for example? I mean, can you talk about those kind of things that you worry about getting there already with proton beams?
Okay, so with any of the designs we have now, I'll start with one that's, I spent a lot of time on in my early career, which is electron cloud instability. So what you have with electron cloud instability, if you have any sort of particle striking the surface of a vacuum chamber, that vacuum chamber will tend to release electrons. Those electrons get accelerated in the fields of a proton bunch going by. So if you have a strong secondary electron yield off a surface, what happens is the proton bunch will come by, it will start to pull those electrons into the beam. The head of the bunch makes it past, but those electrons then go and start interacting further down the beam. This is one of the sources in proton-proton machines of having what we call the head-tail instability. Okay, and so in the head-tail instability, the tail, because there are these extra forces, it starts wagging. It's sometimes called the banana instability because if you go look at it, many of the original things looking at it on the scope, you'd basically see what looked like a banana oscillating back and forth. So in any case, that's
Sorry,
that's
where do the electrons come from again?
The electrons are coming off the surface of the vacuum chambers. And so the issue
surface
is
of the vacuum chamber, just passing through. I see.
Yeah. And so this is a major issue for it was traditionally a big issue in the early days of light sources. There was a big question, which are we better off using, electrons or positrons? So the advanced photon source at Argonne was originally configured to operate with positrons. And the idea was that was, if you go through and look at what's going on, you can say, okay, some physics effects are going to be better for positrons. However, what they very quickly found was because of the synchrotron radiation, the photons striking the vacuum chamber surface released copious amounts of electrons. And then you got all of these electron cloud instabilities.
So then what's the deal?
They
If you have
very
more-
quickly redid their injector so they could work with electrons at that point.
But if you have more particles, higher intensity beams, it's better, just because it's harder to get.
With the higher intensity beams, because of the nonlinear aspects of all of these things, it's you see it more profoundly. Okay, so what has happened since has been to develop vacuum chamber surfaces that have extremely low secondary electron yields. So this, you may have heard of some of these things. You can do an amorphous carbon coating on the vacuum chamber surface. You can, there's another process where if you have stainless steel vacuum chambers, you can create a diamond-like coating on the surface, all of which have reduced secondary electron yields and can knock out the nonlinearity in this important sort of feature. There are other things that matter. So the more traditional electromagnetic sorts of things are having structures in your vacuum chamber where when one bunch goes by and you're in a multi-bunch configuration, you'll create a wake field because of some discontinuity in the vacuum chamber structure. That wake field can be generated by the head of the bunch and impact the tail of the bunch. It's another way to get head-tail instabilities. But more commonly, you'll get what we call the transverse multi-bunch coherent instability, which is in light sources, you'll have a train of bunches. The first bunch will create the wake field, and then it'll interact with the second bunch. And the wake field, if you have a poorly impedance matched structure, you'll end up with resonant buildup of the wake fields down the train. And then instead of it being a head and tail instability of the bunch, it's a head of the train versus tail of the train instability.
Something that you're gonna have with the muons that you don't have with the protons is, I mean, you send it through your lithium hydride or whatever it was.
Right.
You have to get the muons to hit something, roughly once as they pass through.
Yes.
But then there's a jump that you hit left over, what's gonna affect the next muons coming in.
Yeah, so
You don't
what's,
have the, I mean, that's like your vacuum thing, except everywhere throughout the bulk of the material as it's going through.
well, so there's a couple different aspects in this, needless to say. So when you have the muon beam transiting through an absorber, okay, you interact with the electron clouds around the individual atoms and molecules, depending on what material you're using. And so you have your energy loss mechanism. Of course, part of what you're also going to see is interaction with the nuclei. Okay, so you have multiple scatterings. So basically the equilibrium emittance in the simplest approximation is the balance between the multiple scattering effect and the cooling effect. It gets more complicated, for instance, if you want to do this where instead of using, let's say, a solid absorber or even a liquid, you want to use a gas absorber. So we actually did a lot of work at Fermilab using hydrogen gas as the material that was doing the energy loss. Now, that gets more dynamic in the sense that what happens when the beam goes through is you actually ionize the plasma. Okay. That plasma can then do multiple things. One of the things it causes is you've now created a massive charge inside an RF cavity, which is trying to accelerate not only the bunch charge, but whatever plasma charge you have. So the electrons in that case can go and in fact cause a breakdown of the cavity and essentially short out the cavity that way. so we actually did a great deal of work on how you put together, this is a material science experiment. How do you put together the gas mixture properly? Well, if you seed the gas mixture, you have the hydrogen there, but you also include a bunch of electronegative molecules. They can actually soak up the plasma electrons. You still have the ions migrating around, but it completely changes the plasma dynamics. And it actually, at very minimal quantities of these electronegative absorbers, you can defeat the plasma production process at the level where you no longer short out your cavity. So there's a bunch of complicated sorts of things to pursue. The next thing we were starting to look at was, with plasmas formed this way, is what's the dynamic impact on the proton bunches going through, which would have led to exactly the results I've said I'm so interested in getting. It's unfortunate we no longer have access to that beam at the moment. We'd have to do a fair bit of work at Fermilab to regenerate access to it, if you will, but it's well within the realm of possibility.
There are no more questions. Let's thank Mark.